Roger, the Big Bang has now entered common knowledge as the way the universe began, and everybody always asks, how did the Big Bang begin and what happened before that? And philosophers, theologians, physicists now begin to speculate on it. I really come to you because you have some very unique insights into the Big Bang.
But there's something almost paradoxical about this microwave background. It's telling us that there was something like the Big Bang there. But it's also telling us, because the observations of the microwave background, you can plot the frequency, you can plot the intensity against each frequency, and you find this wonderful curve. It's the Planck curve, black body spectrum, and it agrees with that to an extraordinary precision, much better than you could produce in the lab. And this is telling us that the very early universe must have been in what's called thermal equilibrium. Now, thermal equilibrium, by definition, is the maximum random state. It's the state that the second law tells us we're going to get in the future, if you like. But there it is in the past. So why is it that the very special state that has to have been there at the beginning, otherwise we don't have a second law? The second law of thermodynamics tells us things get more and more random, and that tells us you go back in time, things get less and less random. So it must be very, very special in the initial state. But what we find is that the matter, what we're seeing in this radiation is radiation, that's light, and that's been in equilibrium with matter. So that's what you're looking at. And that's at this maximum random state, maximum entropy state, we say. And something special about that was in the gravity. What you're not looking at is gravity. And the thing is that the universe was very, very uniform in the early days. And we think of uniform as, okay, consistent with being random, if you like. But that's not true when gravity is a principal ingredient, because it tends to clump things together. The sun is out there, for instance, because it's clumped together out of a previously uniform distribution of gas. And that sun gets hot. The background sky is cold, the sun is hot. And it's the difference between the hot sun and the cold sky that we live off. And that's where all life comes from that. So that's the key thing. Now, so the universe was very special, but it was very special only in the gravity. Somehow gravity wasn't thermalized with everything else. And that's something which needs to be explained. To me, it's the greatest puzzle about the Big Bang. Now, I don't see most of these theories making any attempt to answer that question. Certainly the inflationary model doesn't. It only, in a certain sense, makes things worse. The argument is that it smooths out the universe and things like this, but it doesn't do that unless you're already special, or even more special in the early stages. So if you follow the argument through, you see that it really doesn't explain this initial specialness. And it can't, because it's all consistent with the second law of thermodynamics, which says things get more and more random. So how could they have got more and more special in the early stages? There has to be something else. Now, for a long time, you see, if anybody had asked me what happened before the Big Bang, I would have given the conventional answer, which is the Big Bang was this singular state when all our equations go haywire and time and space, doesn't make any sense. Even the question before doesn't mean anything, you see. So that's the conventional answer. You say, you can't talk about it. It's just a meaningless question.
There is no before.
There is no before. Now, I now have changed my mind. I'm not sure it's fair to say I've changed my mind, but I have another idea which I'm pursuing, which I think has a reasonable chance of being right. And this depends upon how you characterize the initial state of the universe. So what I'm saying is that the gravity was special. Everything else seems to have been as random as it could be. Now, can you characterize that in some geometrical way? Well, a colleague of mine, Paul Todd, who at the Maths Institute here in Oxford, has had a particular way of characterizing this. I've worried about this for a long time, and I've formulated a thing I call the Weyl curvature hypothesis. Let's not worry about what that means, but it's something about the particular type of space-time curvature that could have been present in the early universe. Now, my colleague Paul has a way of phrasing that in a nice geometrical way, which is to say that you could extend the universe to before the Big Bang. Now, this is just a mathematical statement. You're not saying you believe any physics here. Just saying this mathematical statement. You could extend it before to, as long as you're somehow allowed to stretch the universe out. So I think, what's the best way of explaining this? I think there are some nice pictures that Escher has of everything, a universe of angels and devils, and they're all within this circular boundary. And at the edge, you see, that's infinity. And the whole universe is squashed into this disk. Now, if you forget about the size of those angels and devils and just worry about shapes, then you can, doesn't matter how big they are. The little ones at the edge are the same sort of shape as the ones in the middle. But if you are prepared to stretch and squash in a uniform way, okay, that you could stretch that boundary out to infinity, or you could squash it back to this finite boundary. Now, there is a universe. I mean, the universe in this picture stops at the edge, that's infinity. But you could imagine extending it to the other side and preserving this kind of geometry. It's called conformal geometry. That's a mathematical term, which means that, okay, you know about shapes, small shapes, but you don't know about sizes. So small and big count as the same, but different angles count as different, or different small shapes count as different. So if you don't mind stretching or squashing, then you could step outside this universe to another side to it. So I want you to imagine the same thing here, that you've got the Big Bang, which is somehow stretched out to be a surface, as though that's a one-time surface, but you could go before it. Now, this mathematical trick I'm not saying this is real, I'm just saying it's a mathematical trick. This mathematical trick, if you phrase the condition on your universe in this way, you say you could extend to before, then that is a way of characterizing the initial state of the universe. The universe seems to be like that. It seems to be that the gravitational degrees of freedom are killed off, which is what this picture is expressing. It's hard to say this without being sort of technical, but I hope this sort of idea gets across. Okay, now that's one side of the picture. And if you like, the physical justification for this is that in the very early universe, the temperature was so high, the energies of particles were so high, that it didn't matter a hoot what their masses were. See, mass is what you use if you want to build a clock. There are two fundamental equations in physics that I'm referring to here. One is the famous Planck law, which tells you energy equals E equals h nu. So the energy is proportional to frequency. The other is the famous, even more famous Einstein equation, E equals mc squared, which tells you that energy is proportional to mass. So if you put those two together, it says mass and frequency are basically the same thing. Right. So that means that there's a clock, which is the frequency, is a measure of mass. Now, if you don't have any mass, or if mass becomes irrelevant, you can't build a clock. So in the early universe, the universe didn't know how to keep time, you see. It just it lost track of how fast things were going, you see. And if you take that seriously, you can imagine going to before it. Now, it's a difficult idea to grasp, but it's mathematical. It makes mathematical sense, but it's hard to sort of think this is real physics, you see. But okay, that's one side of it. Now, the other side is think of the very remote future. What do we expect in the very remote future?
We have the universe expanding.
The universe is expanding.
Without limit.
And it's accelerating in its expansion, which is important for this whole picture. It wouldn't work otherwise. And this is this mysterious thing that people worry about. They call it dark energy. Maybe it's just the Einstein's cosmological constant, which is the way I would look at it. But still, we don't know why it should be there, if you like. So, but in this picture, you need it. So I want to say, what's the remote future in this picture? Well, the universe expands. It exponentially expands. And, okay, there's black holes lying around, which have got lots of mass in them. According to Stephen Hawking, these things will, in a very remote future, the universe will cool down to lower than the temperature of any given black hole, even huge ones which have a very low temperature. even huge ones, which have a very low temperature, and they will evaporate away, get smaller and smaller and smaller, and eventually go off with a pop. That's the pic. Now I'm accepting that. I think that's probably right, although there's some conjectural aspects to this. And eventually, all the matter in the universe will disappear, apart from radiation. Now,
very dispersed.
That's right. There's certain assumptions which go into this, but let's accept that there's nothing left but radiation, very dispersed. Now, how do you talk about the very remote future? In fact, the picture I'm trying to describe is a sort of result of my worrying about how boring the universe is. You see, it's going to get pretty boring, you see. And I can't think of anything more boring than waiting around for a black hole finally to disappear pop. You see, it sounds to me incredibly boring. But then I thought, well, who's there to be bored? Not us, you see. The only things around will be these photons and things, and it's pretty hard to bore a photon. A photon doesn't experience any passage of time. So eternity is no big deal to a photon. It just, whoop, there it is, you see. And there's a sort of mathematical trick, another mathematical trick, which I've certainly been involved with for a long time. How do you talk about infinity in relativity, in Einstein's theory, in Einstein's general relativity? How do you talk about infinity? Well, you'd use the same conformal trick. But now, instead of stretching out, which is what I did for the Big Bang before, I'm squashing it down. So I'm saying that in the remote future, there's nothing left which has any mass. If that's the case, somehow the universe doesn't know how to keep time in the remote future. It doesn't know how big it is, you see. So the universe forgets how big it is, in a sense. And it might as well be a small new universe. So the picture, okay, it's crazy.
I followed everything until that very last step where we have a complete expansion, we have complete dispersion, no mass, photon radiations, and the similarity was that there's no clock.
That's right.
Because you have no mass.
That's right.
And that's the same characteristic of the early universe when it was very small.
Yep.
But you have this very big
right.
universe that has no clock. And now how do you get to that small universe that has no clock?
And the point is that it doesn't know the difference between big and small.
Because it has no clock.
It has no clock. You see, okay, you've got the speed of light, which enables you to transform from time to space.
Yes.
But since it's got no clocks, it has no way of measuring distance either. So spatial distance becomes irrelevant, temporal distance becomes irrelevant, or time.
So the universe forgets how big it is.
It forgets how big it is. And so it sort of lost track of that, and it becomes the next Big Bang. Now, of course, this needs to be filled out with some honest mathematics, and it also needs to be related to observation. And the thing is, you might think it's hopeless. How would you ever know whether there was a previous universe, you see? But it's not so hopeless. And the first point is that I mentioned inflation. Inflationary universe is that in the early stages there was this exponential expansion. But in this model, the exponential expansion took place in the very remote future. And that is quite consistent with our present-day view. The universe will expand exponentially. And so you will get same features that you get with inflation, but without inflation. And so then the idea is that that exponentially expanding universe forgets how big it is, and it becomes the Big Bang of the next scale. Now, how do you observe? I mean, as I say, is there observation apart from agreeing with there are these things called scale invariants, which is one of the observational supports for inflation. So I'm saying that I think will carry over to this particular model. Now, the other thing is that there will actually be a little bit disturbances which will come about from, I'll say there'll be in the remote future lots of black holes before they finally disappear with pops. They'll be around for a long time. And in the process, in the middle of galaxies, our own galaxy, for instance, has a black hole in the middle of it of something like 3 million times the mass of the sun. That's quite sort of usual for a galaxy. In galaxies and clusters will, run into each other. Their black holes will spiral around each other, swallow each other up. In that process, they will emit gravitational waves, ripples in space-time, this sort of gravitational analog of light, these ripples will make their mark on infinity. It's a bit hard to explain that one too. But although they get infinitely dispersed, they still, because you have to squash it down again to see what's going on, they're still there. And they will have an influence on the next stage of the universe. And so in principle, and it will require a delicate piece of analysis, you should be able to see that, if I can use an analogy here, think of a pond, and it rains on the pond. Every time a drop of water hits the pond, a ripple comes out. Now that's like these black holes colliding, and a ripple goes out of disturbance and gravitational waves. So you get these ripples. After a while, the rain stops. That's when the black holes have all disappeared, pop, you see. After a while, the rain stops, but you still see the ripples all messy. It looks like just a mess, you see. But in principle, you should be able to work out that these ripples are made up out of individual places where the raindrops have hit. In the same way, I'd say, you could look at this background radiation, and there's now a lot of information from these new satellites and so on, which have been observing the very detailed structure of this background radiation. You should be able to analyze it and see whether it's made up out of these individual events which are spread out in this way. Now that's something for the future. Now, it could completely destroy the whole idea. On the other hand, it might turn out that this is an observation.
I find it absolutely fascinating that it's even possible to consider what happened before the Big Bang.
Well, it's not so outrageous. Okay, it is outrageous, but not so outrageous. It's conceivable that this would work. Yeah. And it does explain the very special nature of the Big Bang, because the whole thing doesn't work without that. So that's I think one positive feature that other theories don't seem to give us.